Discrete Fourier transform. In the chapter, we'll discuss about computations in DFT.
In this session, we'll discuss derivation of DFT equation and cyclic property of Widal factor. Derivation of DFT equation. Discrete Fourier transform is obtained by sampling discrete time Fourier transform. So, by definition of discrete time Fourier transform, x of omega equal to summation of x of n e raised to minus j n omega. Replace this omega by 2 pi k by n. Left hand side omega replace it by 2 pi k by n. Right hand side summation of x of n e raised to minus j n omega, omega replace it by 2 pi k by n. Since left hand side n is constant, 2 pi is constant and a variable is only k, for simplicity we will write only k. So left hand side in terms of variable parameter, that is k. Right hand side e raised to minus j 2 pi by n, will take it common, and outside it will be only nk. Let's represent this e raised to minus j 2 pi by n by a new term, that is wn raised to 1, and by substituting we get x of k equal to summation of x of n wn raised to nk, where n varies from 0 to n minus 1. This w term is called Widal factor. So let's take one example of x of n. X of n is 1, 2, 3, 4. We have to find x of k. Start by definition of DFT. Expand the summation term. For n equal to 0, x of 0, n equal to 1, x of 1, and so on. Substitute value of x of 0, that is 1. W of 0 is always 1. X of 1 is 2. X of 2 is 3, and so on. This equation we have to evaluate for every value of k, starting from k equal to 0. When k is 0, we get x of 0. That is equal to 1 plus 2 into wn raised to k, but k is 0, wn raised to 0 is 1. wn raised to 2k, k is 0, that is 1. And therefore, x of 0 equal to 1 plus 2 plus 3 plus 4. Always remember, DFT first value is always sum of all the input numbers. To find x of 1, put k equal to 1. 1 plus 2 wn raised to k, k is 1, plus 3 wn raised to 2, plus 4 wn raised to 3. Now we need to evaluate this w term, calculate the value of w term, and then we'll have to substitute here. So to start with wn raised to 1, by basic definition of Widal factor, wn raised to 1 is e raised to minus j 2 pi by n. Here capital N is 4. So wn raised to 1 is e raised to minus j pi by 2. That is cos pi by 2 minus j sin pi by 2. Cos pi by 2 is 0, sin pi by 2 is 1, and by substituting we get wn raised to 1 equal to minus j. Similarly, wn raised to 2. Now we can easily calculate wn raised to 2 by basic definition of w, that is in terms of e raised to j term. But instead of going that, we can write this wn raised to 2 in terms of wn raised to 1 like this. Whereas wn raised to 1 is minus j. So minus j into minus j is j square, that is equal to minus 1. And this way we can calculate wn raised to 3 as well. wn raised to 1 into wn raised to 2, that is minus j into minus 1, that is j. So put wn raised to 1 equal to minus j, wn raised to 2 equal to minus 1, wn raised to 3 equal to j. By solving this, we get x of 1 equal to minus 2 plus 2j. Similarly, to find x of 2, put k equal to 2 in this equation. When k is 2, we get 1 plus 2 wn raised to 2 plus 3 wn raised to 4 plus 4 wn raised to 6. Now here we'll have to substitute this w term. wn raised to 2 we have already calculated, that is minus 1. W is to 4, we have not done it, but we know that W is to 4 is W is to 2 into W is to 2. That means minus 1 into minus 1, that is plus 1. And W is to 6 is W is to 2 into W is to 4, that is minus 1 into 1, that is minus 1. So x of 2 is minus 2. Similarly, x of 3, that is minus 2 minus 2g. And if you calculate next value, you'll get first value repeated. What does it mean? DFT produces periodic results. Because DFT results are periodic, we don't need to calculate up to infinity. We just need to calculate DFT value only for one period, and here period is the length of input signal, that is equal to 4. So we have to calculate only 4 values, and these 4 values are 10, minus 2 plus 2j, minus 2, minus 2, minus 2j. Cyclic property of pedal factor W. First we'll do it for n equal to 4, then we'll repeat this for n equal to 8. We know that for n equal to 4, there are 4 unique values of pedal factor. First one is W is to 0, that is always 1. Second is W is to 1. We just now did this calculation. We got W is to 1 equal to minus j. To remember this, take one circle diagram, divide this circle into 4 parts. Horizontal line is real axis, vertical axis is imaginary axis. Because this is unit circle, this will be 1, minus j, j. W is to 0 is 1. W is to 1 is minus j. W is to 2 can be easily obtained from W is to 1, that is minus 1. And W is to 3 is j. So we can write those values on this circle diagram, and we get this pedal factor which is periodic in nature from this circle diagram. So this is W is to 0, W is to 1, W is to 2, W is to 3, W is to 4, W is to 5, W is to 6, periodic, repeated again and again and again and again. The same concept applies for inverse values of pedal factor. Pedal factor negative power is also periodic, but in anti-clockwise direction from this circle diagram. For n equal to 8, we have to go by basic definition of pedal factor and calculate these values of W is to 0, W is to 1 up to W is to 7. Those values we can remember on the circle diagram. Take one circle, divide the circle into 8 parts. This is unit circle, though this value is W is to 0, this is W is to 1, W is to 2, W is to 3, and so on. On this circle diagram, we can remember this. This is 0.707 minus j 0.707. This is both real and imaginary part negated. So minus 0.707 minus j 0.707. This is real part negative, imaginary term is positive, and here both the term positive. This fraction part is same everywhere. Whereas this is 1 minus 1, j minus j. So the pedal factor can be easily obtained from this circle diagram. For negative values, we have to go anti-clockwise direction. When we have taken x of n equal to 1, 2, 3, 4, we got x of k equal to 10, minus 2 plus 2j, minus 2, and minus 2 minus 2j. But what is the significance of this value? So to interpret this value, we will write every value of x of k in terms of frequency term, that is omega. In DFT, omega is always 2 pi k by n. Here capital N is 4. So omega is pi by 2k. When k is 0, omega is 0. When k is 1, omega is pi by 2. When k is 2, omega is pi, and so on. That means these are coefficient value for these values of omega values. DFT converts sequence from time domain to frequency domain. This x of k is defined in frequency domain and signal values are defined in time domain. I converted these values in polar form. When it is in polar form, we can plot this magnitude value and phase value for every value of omega, and if you do that, these magnitude values are 10, at omega equal to 0, 2.83 at omega equal to pi by 2, 2 at omega equal to pi, and 2.83 at omega equal to 3 pi by 2. If you repeat this calculation, you'll get next value 10. So we are getting these discrete values of x of k, but the spectrum is continuous. So we'll have to join this point and get the approximation of this original spectrum. The same concept applies for phase spectrum. Plot the points, join the points for every value of omega.
Thank you.